First of all, thank you so much for having me on this amazing event. I am so grateful for all the team who made this happen, and I'm proud of everyone. I'm proud of all the entrepreneurs and all the speakers and everyone who actually took part in this event. Today, I'm going to try and summarize this in a way that wouldn't be taking too long. I work at the University of North Texas. I'm a lecturer and a researcher. I gained my PhD last year, 2019. And my work has always been on solar energy. I've been fascinated by solar energy, and I wanted to continue doing more research work on this. So that's what led me to do the solar water desalination system using Fresnel lenses. And it's a collaborative work between the University of North Texas and Solar Solutions. I first wanted to actually introduce what is a Fresnel lens in the first place. A Fresnel lens, it was a lens invented by the French scientist Augustin Fresnel. It is nothing but the basic concept of cutting concentric prisms into the regular convex concave lens and made it in a shaped way, in a shaped groove way. You see, number one is actually the Fresnel lens, and number two is a regular lens. The first use for this was in a lighthouse back in the 1800s, and it is still standing till now. The current applications where, if you remember those big TVs that we had back in the 1990s and 80s, those had huge Fresnel lenses using them. So we use them in TVs, cameras, telescopes, and we recently started using them in concentrated photovoltaics, which is a huge research topic these days. We also use it in high temperature applications such as melting, solar cooking, and so on and so forth. All those areas are also under research, and a lot of entrepreneurs have been taking action to patent a lot of Fresnel lens related technologies. So many advantages actually related to Fresnel lenses. The first one is it's compact, so the thickness can be about 1 millimeter, and it is very thin. It is lightweight, so a 1 meter squared lens can be about 1.5 kilograms. That lens, that 1 meter squared lens, can give you the melting temperature of 3,000 Fahrenheit. With respect to it's about 1650 Celsius. And it can give you a concentration power of 2,000 times the actual optical view. It has a very shorter focal length, so instead of like placing the object far away from the lens, now you can place it closer to the lens, which saves space. And it has a very amazing design flexibility. It is a flexible lens in itself because it's made out of plastic. You can just do it or make it in any shape you want. And it has a very much lower cost than regular, for instance, parabolic troughs, because it's made out of plastic, this is abundant silicon that's available anywhere. I decided to make this presentation into three parts. The first two parts are actually talking about the research that we have done over the past couple of years that led us to the desalination project. The first topic is research that we did on using statistical algorithms and artificial intelligence to actually design Fresnel lenses. So we looked at optics from a completely different perspective. This is a paper that we published with the ASME community, and we presented in Solar Power International Conference in California and with the Arab American Association of Engineers and Architects. I'm actually presenting it here right now. So I'm going to try to simplify the concept as much as I can. The basic idea was to introduce what we call the entropy of light. I know I myself used to be terrified of the term entropy when I was doing my mechanical engineering degree, but entropy is just the orderness of things. So entropy is in everything that we have around us, and we wanted to project it on light. So let's say I have 1,000 watts per square meters of incident light. So we assigned a specific number. It's the reciprocal of Avogadro's number, 10 to the power 23 rays to each 1,000 watts per square meters. And this is a bundle of rays coming down onto the Earth. And each one of those rays can be incident in as many as 5 times 10 to the power 8 states. What do we mean by states? It is the combination of different properties of those rays: wavelength, incident azimuth, the tilt of the lens, and so on and so forth. So the conditions that each ray would be incident on, it's as many as 5 times to the power 8. So what we did was we would consider each state of each ray, and we would trace it through the lens onto the focal spot, and we test if that ray state is actually incident on the receiver. So we would make counter, and each time this ray state would be incident on the focal spot of the lens, we would hit one more on the counter. So then we would count all the ray arrivals on the receiver and then convert it into a cumulative distribution function that would eventually be transformed into a heat flux. So doing this, we would be able to calculate what is the heat flux on the focal spot of the lens. And that was the basic idea that we did. I'm trying to actually cut it short to get to the third part, which is the part of the presentation today. The second part is we use that statistical algorithm, and we decided, well, what if I wanted to start a business out of this? What if I wanted to design lenses for people for their different applications? What can I do? So we did what we called the application-based design of Fresnel Lens solar concentrators. If I wanted to, let's say, to burn wood, if I wanted to weld steel, if I wanted to just heat some pool, I would be able to design a Fresnel lens that would do just that using this research. So this is a journal paper that we've published, and we've had the privilege to be awarded with this research. And we also presented in the World Energy Conference and Expo of the AAE. So for the second part, we introduced what we named the genetic-themed hierarchical algorithm, which means we're trying to represent the different parameters of the lens design into different genes. So each value of the lens design parameters, we call it a gene. And then we had those in a hierarchy, level 1, 2, 3, down to 5. Each level represents a different parameter. So we would have for each level like a certain, I would say, interval from a minimum value to a maximum value. I'm not going to go into very detailed explanation, but the basic idea was from each level we would take one gene and we would create a chromosome, and that chromosome we would try and test it if it would meet the required heat flux or the required heat for the specific applications. What does that mean? This is how detailed the algorithm can be, but we would take each of the chromosomes that we've designed and we would make a lens with it. So remember, this chromosome is actually lens parameters. So we would create a lens and we would simulate it, see if it actually would generate the amount of heat that we need on the focal spot. If it does, that's it, we terminate the iteration. If it doesn't, then we would go and start changing or mutating these genes. We will mutate one gene, two genes, as many as we need until we reach the required heat flux. So that was the idea of the GDHA and that we used to proceed with our research. Some applications that we used for this was welding of steel. So we used a lens to weld steel. That sounded, I would say, strange to me when I first started it, but let me show you how it works. Let's say somebody comes to me and wanted to weld those two pieces of steel, 3 centimeters by 6 centimeters, and they're half a centimeter in thickness. So I would use my GDHA algorithm to actually design the lens that would do just that. Now here you can see that the lens needs to be 1 meter and 20 centimeters in diameter, with a focal length of 1 meter and 15 centimeters, certain number of grooves, and which will have an overall optical efficiency of about 76%. And then I would simulate this lens with the specific application, and I would see how the trajectories of those different rays would actually be nicely focusing on the lens, on the focal spot itself. And you can see how the focal spot here, which is the welded specimen's temperature, it's reaching about 2000 Kelvin in a 15 millimeter diameter focal area, which is the welding area of those specimens. We can also see how with the simulation we have very amazing or very nice, I'm not going to say amazing, very nice convergence of the temperature to the operating temperature of steel welding. Then we wanted to see how can the heat penetrate this steel specimen until it reaches the full molten salt within 120 seconds. So within 2 minutes, you should be ready to start moving your specimen and welding it with the lens. Very quickly, we did also another application of a Stirling engine. It's one of the most basic engines we have in mechanical engineering. It just converts heat from any source into power. This is a 64.4 watts Stirling engine that was used to power a submersible pump, a very small submersible pump. We wanted to have its heater at 425 centigrade. So we again inputted the parameters into the GTHA. We designed the lens, simulated it with the Stirling engine cavity, and eventually reached the safe operating temperature within 820 seconds. So we found out through the simulation and through experiment that we can actually we can do this honestly as a business. So those two parts of our research actually led us to think about, well, how can we do something for the community? How can we help rural areas and crisis areas or refugee camps, for instance, through the big crisis of the scarcity of potable water? So this is the research that I wanted to talk about today. Briefly, it is the solar water desalination system using the Fresnel lenses that we've been talking about. It is, again, funded by Solar Solution. Solar Solution is a company founded, actually, its CEO is Mr. Khalid Al-Kurd. He has immigrated from Jordan to the United States, and since then he has two companies, Solar Solutions and LVL2 Charging. Mr. Khalid and UNT, they've partnered to do this research to help the rural areas and probably project the results onto an operational system here in Jordan. So the objective, obviously, was to build a hybrid Fresnel lens and PV-based solar device that can distill water into potable water, salt water we're talking about here, not sewage water. We need to get rid of all the germs and microbes from the other types of water. The concept of distillation is not new, though. It can be very slow, energy intensive, and expensive. That actually what motivated us to do this project. So we wanted to make a self-sustaining system with little to no maintenance, modular, scalable, deployable to disaster areas or where water is scarce. And we needed to use any saltwater source available, such as seawater, river water, and so on and so forth. So the motivation, obviously, was to provide potable water for areas like crisis areas where we have floods and such, where we have refugee camps like the Zatari in here in Jordan, and for areas where we have scarcity of water, like in Africa, even here in Jordan too. So the basic idea of the system was to use the sun energy to evaporate water from salt water, and using this system that we've designed, this is just an early sketch of the system, and convert that steam into potable water to be used by consumers. The mission was to create the system and make it as efficient, scalable, sustainable, affordable, and portable as possible. We wanted to make it efficient to minimize the energy loss by 13% using heat recovery, and we also wanted to make it with a very high water recovery of more than 80%. Scalable, we wanted to make it as scalable as it can be, so any kind of user would be able to acquire it, small or large scale users. Sustainable, using their energy from the sun, either by using Fresnel lenses or PV electricity, so it has a hybrid heater that works on both. And we wanted to make it affordable with a payback period of less than 6 months, no more than that, no operational costs, just routine cleaning that is required. And we wanted to make it portable, so we designed it to be modular. Each and every part can be disassembled easily and quickly and transported to a different area. This is a quick glimpse of what do we have as of the desalination methods that are used around the world. I'm not going to go into details. I'm just going to mention all of them here. Most of them here. Those are not, I would say, heating or evaporation based, or those are just conventional. such as the reverse osmosis, the forward osmosis, membrane distillation, reverse electrodialysis, and the nanofiltration. We've studied almost all the available methods, and we've also studied the evaporative desalination methods, such as the multi-stage flash and the solar humidification, dehumidification. Those are the two methods that are related to our system. The problem with those methods, I'm not going to say problems, maybe the challenge with those methods is the size of the system itself, plus the cost of water from those systems. So actually, the initial cost of those systems is not as I would say cheap or affordable as it should be for a desalination system. So we wanted to choose some of those conventional applications, and we wanted to compare our work. We wanted to make them our, I would say, competitors, if you want to call it that. Doing our research. So we get to the point where we talk about our system. Our system has this is just a sketch of the system itself. It is under fabrication. We're finalizing the simulation right now. So the idea is to get the salt water from any source available here through an intake pipe, and then we would get it through a heat exchanger just to preheat it before it goes into a heat chamber. That heat chamber, as you can see on top of it, there are Fresnel lenses that heats up the water and evaporates it, and then it goes to a heat recovery and condenser where the steam that actually was produced would be condensed and converted into a potable water that goes into a reservoir for end users. So if we wanted to make a closer look on the evaporator or the heat element itself, it has a dome-shaped Fresnel lens at the top where it has a 2D solar tracking system. And at the bottom, you have the salt removal tray. It can be either automated or maybe it can be manual. And we have a saltwater return line. If not, all the water would evaporate whenever it gets to the heater. And we have the steam manifold where we would collect the steam from different units and gets it through one manifold through the condenser. A quick overlook on the different simulation and the description of different components of the system. We've simulated Fresnel lens and we've optimized it using the GDHA method that I've talked about before. So we found out that we needed a 70 centimeter diameter dome-shaped lens to do this. This is per 1 gallon per hour. This is just a prototype. And we also were able, this is a Gaussian distribution that represents the focal heat flux at the focal spot. If you can see it here, I don't think the cursor is actually showing, but it would concentrate the light, and it's reducing about 1.8 times 10 to the power 5 watts per square meters on the focal spot of the lens. And you can see how this is the core of the heater. This is heated up to a minimum of 800 Kelvin, which is, let's say, about 500 something degrees Celsius. This is a very high temperature core of the heater that would be required to evaporate water later on. The heat chamber itself, as you can see, we have different views of the heat chamber. It actually consists of an airtight core with a very negligible convective heat losses. And on top of that core, we have a replaceable copper heating element that works with either the lens as a focal spot of the lens or with a heating coil. And inside that airtight core, we have a copper-based thermal pipes to take the heat from the top plate and then transport it into copper evaporative plates. So the water would slide on those plates, and as it slides, it gets heated, and then it evaporates. So the water, we have an insulated shell with stone mineral wool, and so the water gets into, the salt water gets through this pipe, and then as you can see, it just slides over the evaporative plates, and the steam produced would get out of this shell using this output pipe. And eventually we have a flushing port if you wanted to flush the system and just clean it. And at the bottom, remember, we had the tray for the salt removal. The heat chamber, it gets to the operational temperature by about 22 minutes, which is a very fast time. This is at the, let's say, whenever we start our day and the sun is up, It just takes about 22 minutes to start operation. And that's when we have the complete system reach the minimum temperature of evaporation of water. The heat recovery system is also just a very basic shell and tube heat exchanger, but we had modified it to be a condenser too. It has a steam inlet that gets steam at 110 to 130 degrees Celsius from a central manifold, and then we have salt water inlet outlet to just preheat the water before it gets into the heater, and we have the condensate output. That's the potable water that we will get to the reservoir later on. And we also have a 316 stainless steel shell of the heat exchanger, along with the copper nickel saltwater tubes and the copper fins to enhance the heat transfer process. So where are we right now? We're looking at the prototyping part of the project to be done by October 2020. That would include a 1 gallon per hour system. It's a small prototype. That's just to confirm the results of the simulation. And after that, we're collaborating with the Applied Science of the private university. It is between University of North Texas and the Applied Science Private University here in Jordan to do the big scale system fabrication. And we wanted to do this in Dallas, Texas, and also in Aqaba, Bil-Urdun. And in May 2021, we wanted to prepare for the large scale production, where we would have the results to be able to do a comprehensive journal publication and to finalize the patenting of the project. We're very excited to collaborate with the Jordanian team because this is a big problem. The water scarcity is a big problem in Jordan, and that was the initial motivation of the whole project. Thank you so much. These are my contacts. Please hit me up if you wanted to ask me any question. And I'm really happy and I'm really honored to be amongst you and to be able to present my work here. I would want to thank all the whole team back in Texas and everyone who actually supported me and my team to do this research. Thank you so much, guys.